Hi everyone, this is Stephanie Zoghbi, and today I will be presenting experiment 20 called nitrous acid on page 294. In this video, I will be discussing the purpose of the test, why should I do this test, a description of the reactions, how can I identify my unknown, other reactions involved, what can I test for or confirm, and cleaning up procedures, how I can discard of my solution. First, I will be discussing the purpose of the test. The purpose of this experiment is to distinguish between primary, secondary, and tertiary amines. Additionally, it will allow us to know whether the amine we have is aliphatic or aromatic, but this will only be for the primary and tertiary class. There are also some further reactions that I will be discussing that we can do to identify our unknown, such as a test for phenols and alpha amino acids. Now for a description of the reactions. The experiment explores the use of nitrous acid in identifying many compounds. Each class of amine will react with nitrous acid in a specific way and exhibit a specific result, and this is what I will be exploring in this video. Let's explore how we can make nitrous acid in the first place. Sodium nitrite reacts with HCl to give nitrous acid. This is done through the protonation of O- from the nitrite ion, forming the OH group. To do this, we will weigh 0.5 grams of sodium nitrite and dissolve it in 2.1 milliliters of water. Then, we will weigh 0.5 grams of our unknown, or 0.5 milliliters if the unknown is liquid. In another beaker, we will measure 1.5 milliliters of HCl and 2.5 milliliters of water. We will pour the unknown that we previously measured into the solution so it can dissolve. This will form an amine hydrochloride solution. We place this in an ice bath. Now for the positive test for nitrous acid. We pour the nitrous acid solution into the ice-cold amine hydrochloride solution. Then we pipette a drop and we drop it onto the starch iodide paper. If the starch iodide paper turns blue, it indicates the presence of nitrous acid. If you see this blue color, this is an immediate positive test for nitrous acid and it indicates the presence of a tertiary aliphatic amine. The tertiary aliphatic amine will simply be protonated in the acidic environment created to form a soluble salt. This is because the nitrogen has a lone pair of electrons where it can accept a proton. This form is no longer reactive towards any further reactions that we will see later. Now, if we add the sodium nitrite solution and the solution turns a dark orange color, this indicates that we have a tertiary aromatic amine. If we treat 2 milliliters of this solution with 10% sodium hydroxide, you should see a bright green base. This is because we have already formed nitrous acid, which is protonated in the presence of HCl and then loses H2O to form a nitrosyl cation. This nitrosyl cation is very reactive and undergoes electrophilic substitution to form nitroso derivatives. This will take the ortho-para position, but since the tertiary amine is bulky, it will take the para position since it is less sterically hindered. The orange color that you will observe is due to the hydrochloride salt of the C-nitrosoamine that is formed. When adding NaOH, it will turn a green color, which is the C-nitrosoamine. If you did not observe the blue color, nor did you observe the orange color, then you might have a primary aliphatic amine. If upon the addition of the sodium nitrite solution and you observe rapid bubbling or foaming, this indicates the presence of a primary aliphatic amine. Here, the nitrosyl cation cannot do electrophilic substitution since there is no benzene ring. Instead, it will produce an unstable diazonium salt at 0 degrees Celsius, which will spontaneously react with H2O since it is so unstable, and this will give us nitrogen gas, which is what is observed by the rapid foaming and bubbling. It will also give an alcohol, ketone, and alkene. However, if we don't observe any bubbling, we will pipette the solution into a test tube and heat. If we observe gas, this will indicate the presence of a primary aromatic amine. The primary aromatic amine will react with the nitrazole cation to form a stable diazonium salt at 0 degrees Celsius. This will not spontaneously react with H2O since it is stable, and so it needs heat to give the nitrogen gas, which will push it forward. It will also give a phenol and HCl. Now, if we heat this solution and we don't observe any bubbles, but instead we observe a yellow oil or a low melting solid, this indicates the presence of a secondary amine. This pale yellow solid is the N-nitrosoamine. The secondary amine, regardless if it is aliphatic or aromatic, will undergo protonation by the nitrazole cation and then quickly form the N-nitrosoamine due to the intermediate instability. This N-nitrosoamine can be isolated and treated under the Lieberman-nitroso reaction, which will be mentioned in the other reaction section of this video. So now let's see what other reactions are involved. Firstly, we have the coupling reaction. We can pipette 2 milliliters of the cold diazonium salt, which should have been identified as our primary aromatic amine. We add the solution to 0.1 grams of 2-naphthol in 2 milliliters of 10% sodium hydroxide and 5 milliliters of water. A color change to an orange-red will confirm that the unknown is in fact a primary aromatic amine. This is because upon the reaction with sodium 2-naphthol, an azo dye is formed, which is this red color. This will confirm that the unknown is a primary aromatic amine. For the Lieberman's nitroso reaction, we add 0.05 grams of the N-nitrosoamine, which is also our secondary amine that we have identified. We'll also add 0.05 grams of phenol and 2 milliliters concentrated sulfuric acid to a test tube. We warm the solution for around 20 seconds and then cool. A blue color should develop when the solution is cool. However, a red color will develop when the solution is poured into 2 milliliters of ice water. Adding 10% sodium hydroxide will restore this blue color. Now the test for phenols. Adding a crystal of sodium nitrite to 2 milliliters of concentrated sulfuric acid, then we shake it very well until it is dissolved. Adding 0.1 grams of our unknown, the color should change to blue, which will indicate the presence of a phenol. Another indication of the presence of a phenol is upon the addition of a solution to 20 milliliters of ice water. A color change to red should be observed. The blue color will return after the addition of 10% sodium hydroxide solution. This is because the N-nitrosoamine will liberate the nitrous acid in the presence of sulfuric acid. The free nitrous acid will undergo a reaction with the phenol to obtain the yellow 4-nitrosophenol. This will react with excess of phenol to produce phenolindophenol, which is the blue color. This is the same mechanism that is also used for the secondary amine. Finally, the test for alpha amino acids. We measure 0.5 grams or 0.1 milliliters of our unknown and dissolve it in 1.5 milliliters acetic acid and 2.5 milliliters of water. We place the beaker in an ice bath so it reaches a temperature of 0 degrees Celsius. Next, we weigh 0.5 grams of sodium nitrite and dissolve it in 2.5 milliliters of water. Using a pipette, we will pipette the sodium nitrite solution into the dropper and into the solution slowly while shaking. If upon the addition of sodium nitrite, the solution starts to bubble or foam, this will indicate the presence of an alpha amino acid. As shown in the reaction, nitrogen gas is evolved, which is confirmed by the presence of bubbles. This is because it will react with nitrous acid to form an intermediate, which will decompose to give an alpha hydroxy acid and nitrogen gas. Now for some cleaning up procedures. For the primary aromatic amine, we will dilute the solution with 10 milliliters of water and pass it through 5 grams of charcoal. The charcoal should be placed in the non-hazardous waste container and the aqueous solution in the aqueous solution container. Primary and tertiary aliphatic amines will be diluted with water and placed in the aqueous solution container. Secondary amines and tertiary aromatic amines will be isolated by filtration and placed in the hazardous solid waste container. the filtrates will be neutralized with 10% sodium hydroxide and placed in the aqueous solution container. For the other reactions involved, the coupling reaction, we will separate any solids by filtration and place in the organic non-hazardous solid waste container. The remaining liquid will be placed in the aqueous solution container. For the Lieberman's nitroso reaction, we will make the solution basic with 10% sodium hydroxide if not done already, and place the solution in the aqueous solution container. For the phenols, we can directly place it in the aqueous solution container. And for the alpha amino acids, we have to make it alkaline with 10% sodium hydroxide and place it in the aqueous solution container. The references used were a mix of the textbook, scientific literature, and articles I read online. For animations and chemical drawings, I used Chemix and KingDraw, which were all done by me. Thank you for watching my video. I hope it was useful, and good luck in identifying your unknown.